History of steel. The steel industry has grown from ancient times, when a few men may have operated, periodically, a small furnace producing 10 kilograms, to the modern integrated iron and steelworks, with annual steel production of about 1 million tons. The largest commercial steelmaking enterprise, Nippon Steel in Japan, was responsible for producing 26 million tons in 1987, and 11 other companies, generally distributed throughout the world, each had outputs of more than 10 million tons. Excluding the Eastern-bloc countries, for which employment data are not available, some 1.7 million people were employed in 1987 in producing 430 million tons of steel. That is equivalent to about 250 tons of steel per person employed per year, a remarkably efficient use of human endeavor. Primary steelmaking. Early iron and steel. Iron production began in Anatolia about 2000 BC. And the Iron Age was well established by 1000 BC. The technology of iron making then spread widely. By 500 BC it had reached the western limits of Europe, and by 400 BC it had reached China. Iron ores are widely distributed, and the other raw material, charcoal, was readily available. The iron was produced in small shaft furnaces as solid lumps, called blooms, and these were then hot forged into bars of wrought iron, a malleable material containing bits of slag and charcoal. The carbon contents of the early irons ranged from very low, 0.07%, to high, 0.8%, the latter constituting a genuine steel. When the carbon content of steel is above 0.3%, the material will become very hard and brittle if it is quenched in water from a temperature of about 850 degrees to 900 degrees Celsius, 1550 degrees to 1650 degrees Fahrenheit. The brittleness can be decreased by reheating the steel within the range of 350 degrees to 500 degrees Celsius, 660 degrees to 930 degrees Fahrenheit, in a process known as tempering. This type of heat treatment was known to the Egyptians by 900 BC, as can be judged by the microstructure of remaining artifacts, and formed the basis of a steel industry for producing a material that was ideally suited to the fabrication of swords and knives. The Chinese made a rapid transition from the production of low-carbon iron to high-carbon cast iron, and there is evidence that they could produce heat-treated steel during the early Han Dynasty, 206 BC AD 25. The Japanese acquired the art of metalworking from the Chinese, but there is little evidence of a specifically Japanese steel industry until a much later date. Blister steel. In order to convert wrought iron into steel, that is, increase the carbon content, a carburization process was used. Iron billets were heated with charcoal in sealed clay pots that were placed in large bottle-shaped kilns holding about 10 to 14 tons of metal and about 2 tons of charcoal. When the kiln was heated, carbon from the charcoal diffused into the iron. In an attempt to achieve homogeneity, the initial product was removed from the kiln, forged, and again reheated with charcoal in the kiln. During the reheating process, carbon monoxide gas was formed internally at the nonmetallic inclusions. As a result, blisters formed on the steel surface, hence the term blister steel to describe the product. This process spread widely throughout Europe, where the best blister steel was made with Swedish wrought iron. One common steel product was weapons. To make a good sword, the carbizing, hammering, and carburizing processes had to be repeated about 20 times before the steel was finally quenched and tempered and made ready for service. Thus, the material was not cheap. About the beginning of the 18th century, coke produced from coal began to replace charcoal as the fuel for the blast furnace. As a result, cast iron became cheaper and even more widely used as an engineering material. The Industrial Revolution then led to an increased demand for wrought iron, which was the only material available in sufficient quantity that could be used for carrying loads and tension. One major problem was the fact that wrought iron was produced in small batches. This was solved about the end of the 18th century by the puddling process, which converted the readily available blast furnace iron into wrought iron. In Britain by 1860 there were 3,400 puddling furnaces producing a total of 1.6 million tons per year, about half the world's production of wrought iron. Only about 60,000 tons were converted into blister steel in Britain. Annual world production of blister steel at this time was about 95,000 tons. Blister steel continued to be made on a small scale into the 20th century, the last heat taking place at Newcastle, ENG, in 1951. Crucible steel. A major development occurred in 1751, when Benjamin Huntsman established a steelworks at Sheffield, ENG, where the steel was made by melting blister steel in clay crucibles at a temperature of 1,500 degrees to 1,600 degrees Celsius, 2,700 degrees to 2,900 degrees Fahrenheit, using coke as a fuel. Originally, the charge in the crucible weighed about 6 kilograms, but by 1870 it had increased to 30 kilograms, which, with a crucible weight of 10 kilograms, was the maximum a man could be expected to lift from a hot furnace. The liquid metal was cast to give an ingot about 75 millimeters in square section and 500 millimeters long, but multiple casts were also made. Sheffield became the center of crucible steel production. In 1873, the peak year output was 110,000 tons, about half the world's production. The crucible process spread to Sweden and France following the end of the Napoleonic Wars, and then to Germany, where it was associated with Alfred Krupp's works in Essen. A small crucible steelworks was started in Tokyo in 1895, and crucible steel was produced in Pittsburgh, Pennsylvania, U.S., from 1860, using a charge of wrought iron and pig iron. The crucible process allowed alloy steels to be produced for the first time, since alloying elements could be added to the molten metal in the crucible, but it went into decline from the early 20th century, as electric arc furnaces became more widely used. It is believed that the last crucible furnace in Sheffield was operated until 1968. Bessemer steel. Bulk steel production was made possible by Henry Bessemer in 1855, when he obtained British patents for a pneumatic steelmaking process. A similar process is said to have been used in the United States by William Kelly in 1851, but it was not patented until 1857. Bessemer used a pear-shaped vessel lined with ganister, a refractory material containing silica, into which air was blown from the bottom through a charge of molten pig iron. Bessemer realized that the subsequent oxidation of the silicon and carbon in the iron would release heat, and that, if a large enough vessel were used, the heat generated would more than offset the heat lost. A temperature of 1,650 degrees Celsius 3,000 degrees Fahrenheit could thus be obtained in a blowing time of 15 minutes with a charge weight of about half a ton. One difficulty with Bessemer's process was that it could convert only a pig iron low in phosphorus and sulfur. These elements could have been removed by adding a basic flux such as lime, but the basic slag produced would have degraded the acidic refractory lining of Bessemer's converter. While there were good supplies of low-phosphorus iron ores, mostly hematite, in Britain and the United States, they were more expensive than phosphorus-rich ores. In 1878, Sidney Gilchrist Thomas and Percy Gilchrist developed a basic line converter in which calcined dolomite was the refractory material. This enabled a lime-rich slag to be used that would hold phosphorus and sulfur in solution. This basic Bessemer process was little used in Britain and the United States, but it enabled the phosphoric ores of Alsace and Lorraine to be used, and this provided the basis for the development of the Belgian, French, and German steel industries. World production of steel rose to about 50 million tons by 1900. The open hearth. An alternative steelmaking process was developed in the 1860s by William and Friedrich Siemens in Britain and Pierre and Émile Martin in France. The open hearth furnace was fired with air and fuel gas that were preheated by combustion gases to 800 degrees Celsius 1,450 degrees Fahrenheit. A flame temperature of about 2,000 degrees Celsius 3,600 degrees Fahrenheit could be obtained, and this was sufficient to melt the charge. Refining, that is, removal of carbon, manganese, and silicon from the metal, was achieved by a reaction between the slag, to which iron ore was added, and the liquid metal in the hearth of the furnace. Initially, charges of 10 tons were made, but furnace capacity gradually increased to 100 tons and eventually to 300 tons. Initially an acid-lined furnace was used, but later a basic process was developed that enabled phosphorus and sulfur to be removed from the charge. A heat could be produced in 12 to 18 hours, sufficient time to analyze the material and adjust its composition before it was tapped from the furnace. The great advantage of the open hearth was its flexibility. The charge could be all molten pig iron, all cold scrap, or any combination of the two. Thus, steel could be made away from a source of liquid iron. Up to 1950, 90% of steel in Britain and the United States was produced in the open hearth process, and as recently as 1988 more than 96 million tons per year were produced in this way by Eastern Bloc countries. Oxygen steelmaking. The refining of steel in the conventional open hearth furnace required time-consuming reactions between slag and metal. After World War II, tonnage oxygen became available, and many attempts were made to speed up the steelmaking process by blowing oxygen directly into the charge. The Linz-Donawitz (LD) process, developed in Austria in 1949, blew oxygen through a lance into the top of a pear-shaped vessel similar to a Bessemer converter. Since there was no cooling effect from inert nitrogen gas present in air, any heat not lost to the off-gas could be used to melt scrap added to the pig iron charge. In addition, by adding lime to the charge, it was possible to produce a basic slag that would remove phosphorus and sulfur. With this process, which became known as the basic oxygen process, BOP, it was possible to produce 200 tons of steel from a charge consisting of up to 35% scrap in a tap-to-tap time of 60 minutes. The charges of a basic oxygen furnace have grown to 400 tons and, with a low silicon charge, blowing times can be reduced to 15 to 20 minutes. Shortly after the introduction of the LD process, a modification was developed that involved blowing burnt lime through the lance along with the oxygen. Known as the LDAC, after the Arbed Steel Company of Luxembourg and the Centre National of Belgium, or the OLP, oxygen lime powder, process, this led to the more effective refining of pig iron smelted from high-phosphorus European ores. A return to the original bottom-blown Bessemer concept was developed in Canada and Germany in the mid-1960s. This process used two concentric tuyères with a hydrocarbon gas in the outer annulus and oxygen in the center, known originally by the German abbreviation OBM, for oxygen Bodenblasen Maxwet, oxygen bottom-blowing Maxwet. It became known in North America as the QBOP. Beginning about 1960, all oxygen steelmaking processes replaced the open hearth and Bessemer processes on both sides of the Atlantic. Electric steelmaking. With the increasing sophistication of the electric power industry toward the end of the 19th century, it became possible to contemplate the use of electricity as an energy source in steelmaking. By 1900, small electric arc furnaces capable of melting about 1 ton of steel were introduced. These were used primarily to make tool steels, thereby replacing crucible steelmaking. By 1920, furnace size had increased to a capacity of 30 tons. The electricity supply was three-phase 7.5 megavolt amperes, with 3 graphite electrodes being fed through the roof and the arcs forming between the electrodes and the charge in the hearth. By 1950, furnace capacity had increased to 50 tons and electric power to 20 megavolt amperes. Although small arc furnaces were lined with acidic refractories, these were little more than melting units, since hardly any refining occurred. The larger furnaces were basic lined, and a lime-rich slag was formed under which silicon, sulfur, and phosphorus could be removed from the melt. The furnace could be operated with a charge that was entirely scrap or a mixture of scrap and pig iron, and steel of excellent quality with sulfur and phosphorus contents as low as 0.01% could be produced. The basic electric arc process was therefore ideally suited for producing low-alloy steels, and by 1950 had almost completely replaced the basic open hearth process in this capacity. At that time, electric arc furnaces produced about 10% of all the steel manufactured, about 200 million tons worldwide, but, with the subsequent use of oxygen to speed up the basic arc process, basic electric arc furnaces accounted for almost 30% of steel production by 1989. In that year, world steel production was 770 million tons. Secondary steelmaking. With the need for improved properties in steels, an important development after World War II was the continuation of refining in the ladle after the steel had been tapped from the furnace. The initial developments, made during the period 1950 to 60, were to stir the liquid in the ladle by blowing a stream of argon through it. This had the effect of reducing variations in the temperature and composition of the metal, allowing solid oxide inclusions to rise to the surface and become incorporated in the slag, and removing dissolved gases such as hydrogen, oxygen, and nitrogen. Gas stirring alone, however, could not remove hydrogen to an acceptable level when casting large ingots. With the commercial availability after 1950 of large vacuum pumps, it became possible to place ladles in large evacuated chambers and then, by blowing argon as before, remove hydrogen to less than 2 parts per million. Between 1955 and 1965, a variety of improved degassing systems of this type were developed in Germany. The oldest ladle addition treatment was the Perrin process, developed in 1933 for removing sulfur. The steel was poured into a ladle already containing a liquid-reducing slag, so that violent mixing occurred and sulfur was transferred from the metal to the slag. The process was expensive and not very efficient. In the post-war period, desulfurizing powders based on calcium, silicon, and magnesium were injected into the liquid steel in the ladle through a lance using an inert carrier gas. This method was pioneered in Japan to produce steels for gas and oil pipelines. Alloying. Alloying elements are added to steels in order to improve specific properties such as strength, wear, and corrosion resistance. Although theories of alloying have been developed, most commercial alloy steels have been developed by an experimental approach with occasional inspired guesses. The first experimental study of alloy additions to steel was made in 1820 by the Britons James Stoddart and Michael Faraday, who added gold and silver to steel in an attempt to improve its corrosion resistance. The mixtures were not commercially feasible, but they initiated the idea of adding chromium to steel, see below stainless steel. Hardening and strengthening. The first commercial alloy steel is usually attributed to the Briton Robert F. Mushet, who in 1868 discovered that adding tungsten to steel greatly increased its hardness even after air cooling. This material formed the basis of the subsequent development of tool steels for the machining of metals. About 1865, Mushet also discovered that the addition of manganese to Bessemer steel enabled the casting of ingots free of blowholes. He was also aware that manganese alleviated the brittleness induced by the presence of sulfur, but it was Robert Hadfield who developed, in 1882, a steel containing 12 to 14% manganese and 1% carbon that greatly improved wear resistance and was used for jaw crushers and railway crossover points. The real driving force for alloy steel development was armaments. About 1889, a steel was produced with 0.3% carbon and 4% nickel. Shortly thereafter, it was further improved by the addition of chromium and became widely used for armor plate on battleships. In 1918, it was found that this steel could be made less brittle by the addition of molybdenum. The general understanding of why or how alloying elements influence the depth of hardening, the hardenability, came out of research conducted chiefly in the United States during the 1930s. An understanding of why properties changed on tempering came about in the period 1955 to 1965, following the use of the transmission electron microscope. Microalloyed steels. An important development immediately after World War II was the improvement of steel compositions for plates and sections that could readily be welded. The driving force for this work was the failure of plates on the Liberty ships mass-produced during the war by welding, a faster fabricating process than riveting. The improvements were effected by increasing the manganese content to 1.5% and keeping the carbon content below 0.25%. A group of steels given the generic title high-strength low-alloy, HSLA, steels had the similar aim of improving the general properties of mild steels with small additions of alloying elements that would not greatly increase the cost. By 1962, the term microalloyed steel was introduced for mild steel compositions to which 0.01 to 0.05% niobium had been added. Similar steels were also produced containing vanadium. The period 1960 to 80 was one of considerable development of microalloyed steels. By linking alloying with control over temperature during rolling, yield strengths were raised to almost twice that of conventional mild steel. Stainless steels. It is not surprising that attempts should be made to improve the corrosion resistance of steel by the addition of alloying elements, but it is surprising that a commercially successful material was not produced until 1914. This was a composition of 0.4% carbon and 13% chromium, developed by Harry Burley in Sheffield for producing cutlery. Chromium was first identified as a chemical element about 1798 and was extracted as an iron-chromium carbon alloy. This was the material used initially by Stoddart and Faraday in 1820 in their experiments on alloying. The same material was used by John Woods and John Clark in 1872 to make an alloy containing 30 to 35% chromium. Although it was noted as having improved corrosion resistance, the steel was never exploited. Success became possible when Hans Goldschmidt, working in Germany, discovered in 1895 how to make low-carbon ferrochromium. The link between the carbon content of chromium steels and their corrosion resistance was established in Germany by Philipp Monartz in 1911. During the interwar period, it became clearly established that there had to be at least 8% chromium dissolved in the iron matrix, and not bound up with carbon in the form of carbides, so that on exposure to air a protective film of chromic oxide would form on the steel surface. In Burley steel, 3.5% of the chromium was tied up with the carbon, but there was still sufficient remaining chromium to confer corrosion resistance. The addition of nickel to stainless steel was patented in Germany in 1912, but the materials were not exploited until 1925, when a steel containing 18% chromium, 8% nickel, and 0.2% carbon came into use. This material was exploited by the chemical industry from 1929 onward and became known as the 18/8 austenitic grade. By the late 1930s there was a growing awareness that the austenitic stainless steels were useful for service at elevated temperatures, and modified compositions were used for the early jet aircraft engines produced during World War II. The basic compositions from that period are still in use for high-temperature service. Duplex stainless steel was developed during the 1950s to meet the needs of the chemical industry for high strength linked to corrosion resistance and wear resistance. These alloys have a microstructure consisting of about half ferrite and half austenite and a composition of 25% chromium, 5% nickel, 3% copper, and 2% molybdenum. Forming in casting. The early metal shapers, the smiths, used hand tools to form iron into finished shapes. Essentially, these consisted of tongs for holding the metal on an anvil and a hammer for beating it. Converting an iron bloom into a wrought iron bar required considerable hammering. Water-driven hammers were in use by the 15th century in Germany, but heavy hammers capable of dealing with 100-kilogram blooms came into use only in the 18th century. Slitting mills for making thin strips that were then fabricated into nails were introduced about that time, as were rolling mills for converting bars into flat plates. Grooved rolls for producing rods from puddled iron were patented by John Purnell in 1766. These were powered by a 35-horsepower water wheel. Casting. Steel forming operations were on a relatively small scale until the introduction of the Bessemer process, in which large volumes of liquid steel were produced for the first time. The liquid metal was poured from ladles into large cast iron ingot molds with an average size of 700 mm in square section and 1.5 to 2 meters in length. Such an ingot would weigh about 7 tons. After solidifying, the ingot was stripped from the mold, reheated, and then reduced in size by hot rolling in a primary, blooming, mill to give billets about 100 mm in section. The billets were sheared into 3 to 4 meter lengths, and these formed the starting material for rolling into bars, beams, rods, and strip. This type of billet production persisted until the 1960s, when a profound change occurred with the development of continuous casting machines. With liquid steel going directly from the furnace into the casting machine, there was no need to pour large ingots or to reheat them with heavy energy requirements. Nor were the very expensive blooming mills required for reducing the ingots to forms that were now produced directly by casting. Continuous casting was first used for nonferrous metals in the 1930s, and in the early 1950s experiments were undertaken with it at steel plants in Britain, the United States, and the USSR. The first production plant using continuous casting was operated at Barrow, ENG, by the United Steels Company. In 1965, 2% of total steel production was continuously cast. By 1970 this had risen to 5%, and, by 1990, 64% of all the steel produced in the world was continuously cast. In Japan it was more than 90%. Continuous casting was partly responsible for a new type of steel plant that developed after 1970, the so-called mini mill. Their steel was made in an electric arc furnace using an all-scrap charge and was then continuously cast into small diameter billets for rolling into rods or drawing into wire. Mini mills were built in industrial regions where scrap arises, whereas the location of conventional steel plants remained linked to the availability of iron ore and low-cost energy. Tubes. With the development of the gas industry at the beginning of the 19th century, an increased demand developed for tubes to transmit gas. In 1824 a method for pressure butt welding of heated, curved strip was developed in Britain, and in 1832 a plant for producing tubes was established in the United States. Similar processes are still being used to produce seam tubing. An improvement on the hot pressure butt weld was developed in the United States about 1921, when the seam was joined by electric resistance welding. Most seam tubes are still produced this way, including the large diameter tubes formed by spirally coiling a continuous strip and then arc welding the spiral seam. Seamless tubing involved the piercing of a round billet. This process was developed in Britain in 1841. A greatly improved process was developed by the Mannesmann Company in Germany in 1886. This involved rolling the billet longitudinally and at the same time forcing it onto a piercing bar called a mandrel. The method is widely used for both ferrous and non-ferrous metals. Forging. As the size of ingots increased in the late 19th century, large hammer forges were developed that simulated the early blacksmith's hammering action. For really large components, the first press forge was built in Britain in 1861 and introduced into the United States by 1877. In these forges, the upper forging die is pressed against the workpiece on the lower anvil by a hydraulically operated piston. Foundry. The introduction of the crucible process enabled steel castings to be produced for the first time. Steel products were being cast in Germany and Switzerland from 1824, and, by 1855, steel gear wheels were cast in Sheffield. In the United States, steel castings were first produced in Pittsburgh in 1871. The crucible process continued to be the chief melting method until 1893, when the Tropenis converter, a side-blown, Bessemer-type vessel, was developed in Sheffield. Electric melting in acid-line furnaces was pioneered in Switzerland in 1907, and electric furnace melting is now predominantly used for making steel castings. Research on molding sands, which have a great influence on the quality of steel castings, started in the United States in 1919, and this led to the publishing of international standards for molding materials during the period 1924 to 28. X-ray methods for assessing the soundness of steel castings were introduced in the USSR in the 1920s, and magnetic crack detection methods followed in the 1930s. Plates and sheet. Plates are produced by hot rolling, the technology for which developed in the early 19th century. In order to produce sheet from plate, the steel is cold rolled, and, as there is a limit to the reduction in thickness that can be achieved by one pass through a rolling stand, a series of stands are arranged in tandem. The first mill of this type was installed in 1904 in the United States. In making wide, thin sheets, difficulties arise because the small diameter rolls necessary for producing thin material have a tendency to bend in service, giving a sheet that is thicker in the middle than at the edges. The problems were overcome after World War II by the introduction of larger diameter backup rolls. In an extreme case, the cluster mill, each small work roll was backed by 9 larger diameter supporting rolls.